Did did do. It's time, I think. Just about bit rate looks something. Okay. Sweet. Let's begin. This is rocket science for the complete beginner here on the Abelian Group today. So thanks for tuning in tonight. This is our first week for this one, which is just going to get into some basics and preliminaries, and essentially most of it's just going to be talking about one single number, which I think is a pretty good way to start anyway, perchance. So let's find out. So we're going to start with just like a motivational example, and then we'll use that to sort of talk about some of the things, some of the tools that we'll use for dealing with algebra and mechanics and so forth, and then we'll just do some problems and put these ideas to work. So, essentially, why am I doing this? It's basically we're just going to be talking about classical mechanics without calculus, essentially, which you can do. There will be some calculus sort of mixed in there, but not in any sort of difficult way. We'll be using ideas from there, but we won't actually be doing that. We'll be talking about algebraic stuff like polynomials and rational functions and radical functions, and so on and so forth. As well as we'll get into some trigonometry, which is necessary if you want to start doing more interesting stuff. We'll also use analytic geometry, which is just a big word for graphs, really. But it's actually really useful. And in fact, as we'll see even today, we'll start to see it today, more so next time. Graphs actually, looking at these things geometrically is a really good means of getting stuff to be more understandable. Like there's this, it'll also let us basically do stuff that's sort of calculus without actually having to do calculus, which is important. But I think it'll help us derive some equations and so forth that we shall need. And then, the other side of it, the physics, not the math side, is going to be just a bunch of stuff from classical mechanics. So stuff like distance, displacement, velocity, acceleration, momentum, energy, and so on. And then also there'll be some historical stuff probably mixed in. A few other tangents as well as my interest, comes and goes. So yeah, that's essentially what the whole point of all this is. So if you're tuned in, thanks, and I hope you dig it. I hope it's also useful and somewhat entertaining, at least. But whatever. Lest I ramble on forever. Let's look at a motivational example here. And eventually, the goal of this example is to think about gravity horizontally, from a certain way of speaking. And certainly, the default human, I think, response is to think of gravity as a vertical thing, right? Like it pulls us straight down towards the Earth, and that's true. But it's also constant. Like the acceleration due to gravity here on the surface of Earth is essentially exactly the same. Now, if you're up on a giant mountain or down in a valley, it might alter slightly, but it's so small you're not even going to notice the difference. But it's also useful to think about it horizontally. Anyway, so before I ramble on too much, let's look at what this number is. So a sub g, which is that little underscore there, is negative 9.8 meters per second. Or, we can see it a little bit more simplified here, right, as meters per second, just like abbreviated. But that's also the same as meters per second squared, which isn't necessarily a more useful way to think about it, but it's certainly it's a shorter way to type it. But anyway, so if you're anywhere on the surface of Earth, as I'm assuming most of us are, then this is the acceleration you're constantly subjected to. And let's talk about what acceleration even means. So what is all this stuff? I mean, how do we even say it? So we would say the acceleration due to Earth's gravity is negative 9.8 meters per second squared. Or, and I think this is actually a more useful way to say it, it's negative 9.8 meters per second. And so what I want to do is think about those 2 per seconds sort of individually, if you will. So let's just talk about all these even more in detail. So a sub g, right, it's just the acceleration of gravity. And the reason it's negative is because we want negative to symbolize the downward direction. And positive numbers will indicate the upward direction. The same is true respectively for left and right. We'll use left, we'll associate with the negative direction, and right with the positive direction. And this isn't a commentary about one thing being better than any other or anything like that. It's really just a statement about using negative signs to keep track of where we are, right? So because I can differentiate up and down and left from right, this positive and negative sign is a really efficient tool. And essentially what that means is that we can think of this acceleration as a vector. It has both a magnitude, which is that negative, the 9.8 meters per second, I should say, and it has a direction, and that's what that negative sign out in front means, and it means that that direction is downward. And generally, we're always going to think of stuff that's moving up or to the right as positive. Oops, get that out of the way there. And again, yeah, that's the idea, right? We can use this notion of positive and negative to identify direction. Continuing on, we see that meters per second, it's just a measurement of speed, really. We can also talk about velocity, which is slightly different, but that's okay. But what it is it's just a velocity, right? If we think about meters per second, you're changing however much distance over however much time. And then when we divide that again by seconds, what we're really doing now is we're looking at a change in velocity over some period of time. And that's why we obtain this acceleration, right? Because really what this is saying is it's, plain old meters per second is velocity, so because that's a change in distance, right? It's saying we're changing this many meters per second. So then if we change this many meters per second, i.e. This little business here with the 9.8 there, then that means that our velocity is gaining magnitude of 9.8 meters per second, right? So we're increasing in speed by 9.8 meters per second every second. And then again, the negative just means that that's focused downward. So let's put a somewhat realistic scenario here. Suppose some hooligans, youths, whatever. I don't know. Back when New Girl was good still. Suppose these hooligans are rolling boulders off a 200-meter cliff into the old quarry outside of town. Let's also assume that we don't have to worry about air resistance or anything because that's just bad. Like, you don't want to deal with differential equations. I mean, do you really want to? Like, you might think you do, but I think it's like people like youth who join the military for glory and fortune and stuff, like in the heroic tales of like a century ago, and then like they find out the horrors of war and or blah blah blah. I feel like that's kind of, if you tone that down to where the stakes are much lower, that's essentially solving differential equations. It sounds all cool at first, and then like you're faced with the horrific reality. I mean, they're not that bad, but whatever. So that was sort of a tangent there, but so they're pushing this 200-meter boulder off a cliff, and we're not going to worry about air resistance at all. So let's see if we could talk about like the boulder's vertical velocity, its speed with the direction, as it goes down to the quarry below, right? And much to the delight of the truants who laugh hysterically from atop. So before we even do anything else, let's just sort of heuristically talk about our boulder here. So for example, the instant the boulder leaves the cliff, its speed is 0 because it's neither going up nor down, right? We're looking at its vertical velocity here. And so if the vertical velocity, nothing's happened to it, the instant it's pushed off the cliff, gravity hasn't really had a chance to do anything with it yet, right? So when time equals 0, right, like the instant the boulder is pushed off the cliff, its velocity downward is 0, because there hasn't been a chance for it to accelerate yet. But as soon as the boulder is no longer subject to the upward force of the cliff, which is opposing gravity up to that point, once it's rolled off, gravity is the only thing affecting this boulder anymore. And so it's this constant acceleration speeding the boulder up as it falls down. And we know that it's this constant negative 9.8 meters per second. So that means in the first 1 second after the boulder leaves the cliff, it increases its velocity from 0 meters per second to negative 9.8 meters per second, right? But then over the course of time between the first second and the second second, its speed drops, it increases in magnitude by another negative 9.8 meters per second, right? I mean, that's what that acceleration means. It means that every second that passes, you're going 9.8 meters per second faster than you were before, right? So after 2 seconds, you're going 19.6 meters per second, right? And then the time between the second and third second, you accelerate up to 3 times the acceleration there, right? And this continues until eventually the boulder hits the ground, and at that point the pattern no longer holds, right? Because now there's stuff opposing the force of gravity. There's things, it's on the ground. It can't just free fall anymore. And then again, just to mention it one more time, the reason that negative is there, just like on the acceleration, we see the negative signs showing up on the speed or velocity as well, I should say. And that's because, again, it's going downwards, right? Like we want to consider down to be the negative direction and up to be the positive direction. Just a little orientation, if you will. Words, phrases, good times. So to better formulate our theory of boulders and hooligans, let's sort of look at it from 2 perspectives. In this case, this is a very simple problem. But it's nice to have a couple different approaches to it. So the first will be sort of algebraic, which is very straightforward. Here's a little table of data that we accumulated from our discussion on the last slide. Right? We have the time in seconds since the boulder was pushed off the cliff on the top bar there. And then the second row is the velocity in meters per second, t seconds after the boulder has been pushed off. So just like we saw before, right? It's the instant it leaves the cliff, right? 0 seconds after it's pushed off the cliff, it's going 0 meters per second. 1 second later, it's accelerated to negative 9.8 meters per second, and so on and so on. Yeah. Also, we see there's kind of a pattern here, right? Like it's pretty straightforward if you haven't already seen it, right? I mean, the velocity at any given time is the acceleration of gravity in meters per second squared times the time in seconds, right? For example, this is just 1 times negative 9.8. This is 2 times negative 9.8, and 3 times negative 9.8, etc., etc. Also, this is really important to check out here, too. The units of acceleration are meters per second squared. And then you multiply those meters per second squared times seconds, and just like you would with numbers, like if you were, reducing a fraction, say, you cancel out one of those seconds and you're left with meters per second. So we have meters per second on both sides of the equation, which is good. Otherwise, it wouldn't make any sense. And it's always good whenever you're doing math or physics or anything, I guess, for that matter. But especially in math and physics, you should make sure that your answer makes sense. That might sound silly, but if you get an answer, you get a solution, and you're not sure if it's correct. I mean, you can check. Do the units make sense? Right? Did I perform this calculation here correctly? Well, are my resulting units in meters, or are they in meters per second, or seconds, or meters per second cubed, or whatever? Right? Units can really be a benefit. I'm really thinking of Tropic Thunder there, but it's my unit. Anyway, so that's right. I mean, this is a very simple algebraic. This is a linear function. It's very straightforward. But now let's look at it more geometrically, and to do that, let's introduce the Cartesian coordinates, the Cartesian plane. And as it says there, the same person who brought us cognito ergo sum, I think therefore I am, i.e. René Descartes, is almost as famous for developing the Cartesian coordinate plane. Note its subtle beauty. There before you, a wild Cartesian coordinate plane. So notice that there's a pair of axes there. This might be stuff you've seen before. But the place where they intersect, we're going to call that the origin, and we'll just label that point 0, 0. Now, going back to our notion from the algebraic perspective, where we thought about up being positive, down being negative, we see that's reflected here again, right? We're going to talk about anything above the horizontal axis as positive, and stuff below it we'll view as negative. And similarly, stuff to the right of the vertical axis will be considered positive, and stuff to the left will be negative. Similar, anything going in those directions will follow that same sort of sign chart. And again, like I said before, it has nothing to do with left being better than right, or seeing that, like, going from left to right is the way to be, or anything like that. It's bookkeeping, right? It lets us differentiate as to which direction we're going. So there we go. So let's look at how this is sort of... So we had the plane axes there, which weren't particularly interesting. But here's something more interesting. So here are a pair of axes. Here's a coordinate plane upon which the rain in Spain mainly tends to fall upon. And we can see here, I've labeled some points on this little graph that's sitting on those axes. Notice that I've labeled the horizontal axis with a T, and then just to call it something, I labeled the vertical one S. Now, each of these points, as you can see on this graph, is uniquely identified as an ordered pair of coordinates. And this is very much like finding your location on Earth via latitude and longitude, right? You need an east-west and a north-south to find out where you are. And this is very similar. Here, it's just instead of east-west, we've got our positive, negative, and then that's the t values, and then our north-south is our positive and negative s values. And so what we see here, for example, let's start over here. There's this point, which is a comma 0. Notice that the first point is the horizontal bit, so a is the value, is the distance here between the origin and this point right here on the horizontal axis. The vertical bit is 0 because it's neither below nor above the vertical axis. So that's what 0 is. Here's a similar point. It's very similar, except it's sort of the flip, right? Here, the horizontal component is 0, right? We're sitting right at that intersection point between the horizontal and vertical. And then b is just this height from the vertical, right? So this is the horizontal component is 0. And the vertical component is b, whatever that value happens to be. We don't really care what it is as a number. This is much more about the idea, right? And so if we think back to, let's go back real quick, to our orientation of the plane, right? Stuff that's above or to the right is positive. Stuff that's down or to the left is negative. So if we look at, for example, we see that because a, which is the horizontal coordinate, is to the left of the origin, a has to be less than 0, right? It's negative because 0 is here, and if we move to the left from 0, that means we're going in the negative direction. So a has to be negative. Now, this point isn't negative. It doesn't even make sense really to say a point is positive or negative, but this component, this a, is definitely negative, right? It's less than 0. The same is true for this output value s sub little m over here, right? Where because the vertical component, which is this second part, is below the x-axis, that means that the vertical component has to be negative, right? And that's, again, just going back to this orientation we've devised. There's other things we can say, too, so let's maybe let's maybe write some stuff down. Let's just get some paper out just for good measure, for funsies, you know. Let's do it for funsies. And actually, here, let me move this real quick. Cool. So let's notice that between x, let's just, or so the horizontal axis is t, right? So between t equals 0 and t equals, or actually, yeah, let's do that. And t equals t sub capital M. Well, what is the function doing in between those little parts, right? So we're asking, like, what is this blue thing doing between here? You know, here's where the horizontal component is 0. And then over here is where the horizontal component is t sub big M, right? Well, we could say essentially that, you know, the function is increasing. It's this thing in blue stuff. Right? And that's not too surprising, right? Like if we just follow the blue chart from the point where t equals 0 over here to where t equals m, it goes up, right? It's further positive than it was before. In similar fashion, we say that between t sub big M and t sub little m, it's the exact opposite, right? Like here, the function's dropping over this whole interval, right? Like the whole way in between this point over here and this point right here, the whole time the function's just going down. Yeah. We could also say stuff like, we could do something else. We could say that notice also that, let's see, what's a good one? Oh, so let's just, what's happening between A and C? So what's happening between t equals A and t equals c, right? So we want to know, like, what can we say about the function that's happening in between these 2 points right here? Well, I mean, sometimes it's increasing, sometimes it's decreasing. There's even this little saddle point right here, which I don't know why, but it makes me think about Milton Wadamus from Office Space for some reason. But anyway, but one thing we can say is whatever the hell else is going on, this function is positive all throughout here, right? Like in between these two values, because all the blue stuff is above the horizontal axis, this has to be positive. A better way to say that would be that the function, I probably should have given it a name. Let's call it s of t. We'll talk more about that notation in a second. And let's bring out the, let's just start introducing some notation. So there's the greater than notation, right? Remember the alligator eats the big stuff? Anyway. And there's, I mean, we could continue this, right? We could talk about what's happening between C and T sub little m, or what's happening between A and 0, etc., etc. Incidentally, these big M's obviously correspond to the maximum, and these little m's correspond to a minimum. Notice also that the function changes from increasing to decreasing around the maximum, and it does the exact opposite around the minimum, right? Like it keeps getting smaller, 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 and then the point where it turns around and gets bigger again, that's the minimum. That's the smallest it can get. And we could yap about this all day, but that's not terribly exciting, and I think, you know, doing more examples would probably be better. So here's the Earth. Dang, that's a sweet Earth. So let's talk about these notions about acceleration. What does it accelerate? And let's try and draw a picture of it. I mean, it's already there because I forgot to put /pause in the code. Freaking LaTeX. But anyway, So let's denote the horizontal axis as time since the boulder was pushed off the cliff. And we'll let the vertical axis, represent the acceleration of gravity. And let's notice that I've drawn the gravity there in an orange function down here. Here's our regular old Cartesian plane axes, right? This is our horizontal axis. This is our vertical axis. And right here, this is our acceleration due to gravity, right? I could have had it extend this way. I probably should have. But the important thing to notice here is that, no matter how much time passes, the acceleration of gravity doesn't change. Yeah? So, no matter what you do, no matter how much time passes, the acceleration of gravity won't change. Now, notice here that, eventually, I have this point marked here, t sub ground, and this is to indicate that this is the point in time where the boulder hits the ground after being kicked off the cliff. But notice that, I haven't ever, the acceleration is going to continue. It's always going to be negative 9.8, no matter what. And this is where gravity goes horizontal, right? Because if we view any constant function, a function that never changes, it's always going to be a horizontal line. Because if you think about it, all of these orange dots on this line, think about this line, this orange line as being made up of infinitely many little orange dots. And each one of those orange dots is an ordered pair. And the ordered pair represents the acceleration at a given time t. But because the acceleration is constant, no matter what time t you're at, i.e. no matter where you are horizontally, your vertical component will always be negative 9.8. And so here's how we can graph the acceleration of Earth's gravity. Isn't that exciting? It's a horizontal line. Bruh. So cool, bruh. But despite the fact that this seems sort of trivial and maybe even stupid, dude, we just multiplied that a minute ago. Why are you making me draw pictures and stuff? Well, there's a reason for that. And that's because, and this is where we're gonna just, for the first time, just a smidgen, just to see how it feels, we're just gonna dip our toes into the water of calculus here without calling it calculus. But these ideas that we're gonna start talking about are the sort of foundation of integral calculus. But yeah, so let's look at this graph and let's consider, so suppose we want to know, for example, how fast the boulder is going. In this case, t hat seconds after it's been pushed off the cliff. Now, t hat it's an arbitrary time greater than 0. Who cares what it is? Let's assume that the boulder is still falling at t hat. But we don't care about what number it is, right? So we know from our algebra bit that this is the function, right? It's always going to be negative 9.8 meters per second squared times however many seconds have passed, and in this case, that's t hat, right? And it's called t hat because it's got a little hat on. T fedora, if you will. Anyway, but notice that the height of this rectangle here is exactly negative 9.8, and the width of this rectangle here, because remember, this point here, the origin, this is 0, so the distance between here and here is precisely t hat. So that means t hat seconds have passed. And so from our algebraic formula, we know that it's just the acceleration times the time we were going that acceleration. But what we can see from this picture is that that's exactly the same as the area, the signed area. And what that means is just positive or negative. It's the signed area between our function, our gravity function, that constant horizontal line, and the horizontal axis. And notice that for any time, however much time we want to spend, however much time we want to let this thing fall, it's always just going to be the product of that constant acceleration times the number of seconds. And that's always going to be a rectangle. So that means we can view the velocity of this falling boulder as the area underneath this curve. And not surprisingly, the more time we let pass, the more area that will be filled in here. And that means that the faster the boulder will be going. And so that makes, I think intuitively, that makes perfect sense, right? This is exactly what you would want to have happen, right? Because otherwise, I don't know. It'd just be weird. But isn't this rad? I don't know. I think it's pretty rad. Like, right, we can view velocity as an area between the horizontal axis and acceleration. I think it's rad. Maybe it's not. But I don't care. No. Whatever. Continuing on. So let's take a minute and summarize some of these topics, if we can, if we may, if we might. Come on, brain. Yeah, so we can generalize this, right? I mean, here's our formula, right? So assuming, we have for any constant acceleration, whatever it is, notice there's no sub g here now, this is any old A, that there's any number of possibilities, right? So if acceleration is 10 meters per second squared, then after 2 seconds we're going 20 meters per second, etc., right? So this same formula holds for any constant acceleration, right? It's always going to be the same. We also saw that this relationship is the same, we just saw that in the last slide, that this is the same as like the area between the curve of the acceleration, and the horizontal axis. And we can sort of generalize this notion to, it doesn't just have to be acceleration and velocity, it could be distance and velocity, or the rate at which you sell books and how many books you sell total over a certain amount of time, etc., etc. The most general way I could think of to describe this was just simply, so if you're accumulating stuff, and let's call that stuff S, right? And, the amount of stuff you have is changing at a constant rate, let's call that R. Then the total amount of stuff you have t seconds later is exactly this much stuff, right? It's it's how long you've been gaining stuff times the rate at which you have been gaining it, right? So in the case of our example we did earlier, it's just like, we were accumulating velocity over the course of time through the changing rate of velocity, which was our acceleration, right? And so we can think about, our speed is being accumulated as we continue to accelerate, and this little formula here just tells us exactly how much has accumulated after this many seconds. Yarp, yarp, yarp. Good stuff. Good times. Make it Santori times. So let's do some example problems. These are all pretty easy, I think. But let's just make a little room here. Put this guy over. So, suppose you're traveling at a constant speed of 40 meters per second for 8 seconds. How much distance did you accumulate? Or the better way of saying it is, how far did you go? I forgot the parentheses. But again, so here, right, our general form of this, right, is just this S equals R times T, yeah? But here's a specific case where the stuff we're accumulating is distance, and the rate at which we're doing it is just as our velocity, right? So again, here we have this dart, which all day when I was writing this just makes me think of ODB, man. Wu-Tang forever. Wu-Tang! Wu-Tang! Ooh! Right. Well, we want to know how much... so if we go 40 meters per second times 8 seconds, let's notice here a couple things. For one thing, the units are going to cancel, so these seconds will cancel with these seconds, right? And we'll get 40 meters times just the number 8, right? And this is really good because we know that this here is distance. And we'd better hope that our units end up being of some sort of unit of distance, and they are. And in this case, that's what, 320 meters, I think? Yeah. So again, let's just take a second and step back and make a note here, this answer makes sense. And I think I even mentioned it on this slide, but it's nice to see it again. i.e., there's meters per second on both sides of the equation. Because otherwise, that's no good, right? Then you're saying distance is equal to time or some weird thing like that, and that's probably not true, yeah. Word. Do-do-do-do-do-do. Same thing with the next one, except here we do a little bit different. So you pick up 20 pounds of garbage in 2 hours, so we know that the total amount of garbage you pick up, right, is 20 pounds. And we know that our rate of garbage, right, our rate of garbage is, well, we don't know yet. It's going to be the change in garbage over the change in time. Also, let's make a little side note here. The Greek delta means change in. And so anytime we see delta, just think about the change in stuff, right? So for example, here, right, like this is really our change of garbage, right? Because originally we had no garbage, and then we picked up 20 pounds of it over the course of 2 hours. So we know our time is 2 hours. Yeah, so what we need to find is this rate. Let's call it the rate of garbage collection, or garbage up picking, I think is what I called it. Yeah? So I mean, I realize it's already on the slide, but it's nice to work through it and talk about it. So what is it? Well, we know that the total stuff we accumulate is going to be the rate times the time that we're accumulating it at that rate. And so in this case, that's just, well, we don't know what R is, but we know that we did it for 2 hours. Right? And we know that all told, this is the same as the 20 pounds garbage we picked up. Yeah. And so then we just do a little algebra here, right? We divide both sides by 2 hours. And it's important to divide by the units, right? We want to keep our units straight. And so then R is just going to equal 20 over 2, so that's going to be 10. And then times pounds per hour. What this means is that for those 2 hours you were collecting garbage, you collected it at 10 pounds per hour. That's the rate at which you collected the garbage. You even help your landlady take out her garbage. Mr. Anderson. Anyway, word. So let's do the next one, which is pretty standard there. Right, this is that classic problem that everyone talks about hating, right? Like, oh my god, we have to do the train problem. So, assuming Metropolis and Gotham City are 2,000 kilometers apart, I have no idea how far apart those fictional cities are, but just suppose that's how far apart they are. And let's suppose a train passes Metropolis, traveling 100 kilometers per hour, headed for Gotham. 1 hour later, another train passes Gotham, headed for Metropolis, traveling at 120 kilometers per hour. At what point will the two trains pass each other? So this one's a little trickier, right? It's maybe not quite as trivial, right? It doesn't seem like we can just write... Like for this one, we can't just do a simple, dart McGirt. Ooh, boom, 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 boom. Sorry. Triumph. We can't just do this, right? Because stuff's happening at different speeds and so forth and so on. But one thing we do know is that at some point, we know that the total distance the trains will have traveled is is 2,000 kilometers, right? A kilometer, in case the metric system is new to you, is 1,000 meters. This is the beautiful thing about the metric system. You don't have to know numbers like 5,280 or 12 or whatever. You just move a decimal around. Right, so this is like 2 million meters, I suppose. But anyway, who cares? More importantly, so we also know that before the second train is doing anything, at least in terms of our problem here, there's an hour where the first train is going, but the second one isn't really. So let's call the Metropolis train. Let's call the train from Metropolis leaves an hour early. Right, this leaves an hour earlier than the train from Gotham, which is pretty obvious, right? I mean, it just says it in the statement there, but sometimes it's nice to sort of separate all this. And this, I'm going to use this as my, let's use this to let's break this up. This suggests we should look at that first hour separately. That's my separately abbreviation. The amount of time I'm spending saying this, I could have just written separately. Anyway, so we know that this first, let's just talk about the first hour, right? Let's draw a little picture here. So suppose here's the whole length of track, right? Here's Gotham, right? And here's Metropolis, yeah? So this total distance, we know the total distance is 2,000 kilometers. Yeah? And that's going to be equal. So just where I'm just drawing this mark here arbitrarily. This isn't necessarily. Let me make it clear. This is 2,000 kilometers, right? And I'm going to say this is the point. This little guy right here. This is the point where trains meet. And then at some point even further over, say somewhere over here, right? Because again, the Metropolis train leaves an hour earlier. This is, let's call this purple point. This is the point at which the Gotham train heads towards Metropolis. Right? So what is this? This is the distance that the Gotham-bound train went in 1 hour. So let's call this D1, right? And then the whole rest of this other distance, let's call D2. Yeah. And let's make a seemingly, well, it is kind of obvious, but useful but obvious operation. Notice that D2 plus D1 equals 2,000 kilometers, right? Right? Whatever this distance is, plus the rest of the way gives you the whole thing, right? Like if you have 10 apples and you eat 2 of them, there's still 8 more apples left to eat. But, so for all of this, I mean, I don't know, what's the most important thing here? Like, what can we gain from this? Well, this is the key, as it turns out. In this mind is the key. Mind key. Yeah. So let's look at these 2 different pieces. Let's start with the first distance, yeah? So d1 is the distance the train from Metropolis travels in the hour before the train from Gotham. Well, let's say before the train towards Metropolis departs, right? So d1 is going to be equal to the velocity of train from Metropolis right? So that's whatever that rate is times the amount of time it times the time. Well, but the time is just it's just one, right? I mean, it's just 1 hour. I don't even want to write a whole separate line for that. It seems silly. Yeah. So this is just that dirt McGirt, right? It's d equals the rate of speed times the amount of time you're traveling at that speed. We could go even further, right? I mean, we know the velocity of the train by assumption is what, 40 or 100 kilometers per hour. So it's 100 kilometers per hour times 1 hour, right? So that means that our initial distance, the initial d, if you're into anime, is 100 kilometers, yeah? And we did that in 1 hour. Cool. Believe it or not, this is super useful, and now we're almost done. So now we know, let's go back to our picture, right? We know our total distance is 2,000. And we know that this distance now is 100 kilometers, which means that this distance has to be 1,900 kilometers, yeah? And that's not real surprising, right? I mean, that's heuristic, right? I mean, if there was 2,000 kilometers total to go, and you went 100 kilometers per hour for an hour, that means you knocked off 100 kilometers, and there's 1,900 left. So let's do the next one. Let's do this again. So now we got to calculate d2. Well, we already know what d2 is, but let's use d2 to find the rest of the time, for lack of a better word. Right? We know it's going to take at least 1 hour for these trains to cross because it's only, the other one doesn't even start until an hour after this one has left. So there's no possibility of them meeting in that first hour. It's got to be some time after that, and that's our goal, right? We need to find out, right, how much longer does it, when will these pass each other, right? So what do we know about d2? That's this little guy here. Yeah. Well, we know then that 1,900 kilometers is equal to the rate of speed times the time at which you travel at that speed, right? This is what we need. This we can find. With what we have. Anyway, so continuing on, let's rewrite this out a little bit cleaner here. So we just have to find this. If we can find r, we know that the time, let's even call it time sub d2, right? The time to cover that second chunk of distance, well, that's going to be equal to 1,900 kilometers divided by the rate of speed, right? Whatever that happens to be. But since the two trains are moving in opposite directions towards each other, right? The total speed, this rate of speed, because really this R, to be specific, this is the rate at which the distance is decreasing. Distance between the trains, I should say. Yeah? But R is just equal to the... I mean, think about it. So one train is going at you. So if you think about it, we're on a highway, right? And you're driving next to someone in the other lane, it doesn't feel like your speed next to that car is very fast, right? Like you can look over and it looks like maybe your car is going like a couple miles an hour faster than that car. Even though the two of you are both traveling, like, say you're going 67 and that car is going 65, you're both traveling at high rates of speed, but relative to each other, you're not. On the other hand, when you're on the highway and another car passes you in the other direction, right, then it seems to be going super fast, right, because the distance between you is disappearing at the rate of your speed of travel and the other cars. So this is going to be the R of train Gotham plus the rate of train from Metropolis, right? And we know that the one from Gotham is 120 kilometers per hour, and the one from Metropolis is 100 kilometers per hour. So the total speed, our rate at which the distance between trains is decreasing, is 220 kilometers per hour. And so that's no big deal, right? Now all we have to do is plug that number in here so we know the time for that second distance. Right? And we also know that, remember, t sub d1 is just 1. The time for this second distance is 1900, because that's how many kilometers are left, divided by 220 kilometers per hour. Whoop. There we go. Cool. So let's finish this homeboy up, yeah? So we just need to find this time. Let me get a calculator. 1900 divided by 220 is 8.6364 hours. Now let's be a little careful here. Why is this hours? Well, the kilometers definitely cancel, right? And then also if we have 1 over hours, that's the same as just plain old hours. So the units actually do make sense, right? The time to do that second bit is 8.6364 hours. So the total time is the time for distance 1 plus the time for distance 2, which is 8. Well, I did it backwards, but whatever. 8.6364 plus 1. 1 hour. So 9.6364 hours. Bam! And assuming that's how fast the trains go and how far things are between Gotham and Metropolis, there you go. That's how long it takes. It takes a little over 9.5 hours by train. Beep 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 beep. Skippity beep 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 beep. Right. Finally, this last one you might even know the answer just if you've ever seen Back to the Future, but let's assume you haven't. So here, so we know that the time required is 47 milliseconds. And we know that the rate of power consumption is 2,574 gigawatts. Unfortunately, there's a problem here. It's kind of subtle. Maybe it's obvious. I don't know. The problem here is our units. Yeah, there's a unit disagreement, right? So our rate. Oh, whoops! I forgot to write. That's per second. And that's really where the problem rolls in, right? Because our rate is in gigawatts per second. And our time is in milliseconds. So what we need to do is a little conversion. So let's note that 1 millisecond equals 1 over 1,000th of a second. Another way to say this is that 1,000 milliseconds is 1 second, right? Mil is like Latin. It's like the Latin suffix or prefix rather for 1,000, right? That's like why a mile is a unit of distance. It's approximately 1,000 paces, which is roughly right. Like most humans have about like somewhere between like a 5 and 6 foot stride. So if you think about 1,000 times about a 5.5 foot stride, it's about 5,280. Oh, room. Whatever. Cool, so what does this mean? All right, so blah, blah, blah. So that means that there's two different ways we can do it, but I think maybe the easier way is, 2574, I'm just going to abbreviate gigawatts with a GW there, per second, right? Well, there's two options. We can either change T into regular seconds, or we can turn R into gigawatts per millisecond. Yeah. So let's just do it this way. Let's just change milliseconds into regular seconds. So that means 47 milliseconds divided by 1,000 milliseconds per second. Notice again, the milliseconds will cancel and we'll get 1 over seconds. And this one isn't even that hard. I mean, you could get a calculator here, but it's not necessary, right? Like we're dividing by 1,000. So what does that mean? Well, that just means we're just changing decimal places, right? Like dividing by 1,000 just means move the decimal place over, 1, 2, 3 places. So, doop, doop. Yeah, so this is 0.047 seconds. Yeah. And so in this case, our total power required is, well, it's the rate of power consumption, bam, times the amount of time you're consuming at that rate. So that's going to be 2,574 gigawatts per second times 0.047 seconds. Again, notice this cancels, and if you do a little multiplication, you get what it should be. 1.21 gigawatts! 1.21 gigawatts! Tom, it's not possible! Is it? It can't be done! No! Whatever. Word. Well, that's week 1. So to the two of you watching, thanks. For the two of you who aren't watching, whatever, you're not watching, so you don't even know what I'm saying. But yeah, that's the spiel for this evening. I'll probably post some stuff on my website and actually put links up to that at some point this week. Not that anyone's watching, but anyway, if you were, that would happen. Anyway, thanks so much for tuning in. We'll see you next time on the next go-around. Have a fine evening.